problem 3. Okay, so this is a thin problem. It says consider a solid cylindrical rod of radius r and length L. Oops. Okay. Length L. Between two walls as shown in the figure, at the connection between the first wall and the rod, which is z is equal to 0, a constant heat flux Q0 is applied. Okay, while the other end of the rod, z is equal to L, the temperature is kept at TL. Air at T infinity is passed over the rod. Okay, and the heat transfer coefficient between the rod and the air is H. Assume that the thermal conductivity of the rod material is K. Okay, and can be considered constant. You can also assume that the temperature of the rod is uniform for a given Z position. In other words, the temperature is not a function of radial position. Okay, good. Obtain a relation for steady state temperature distribution in the rod. So as we did in the thin problem, you should get actually a very similar differential equation. You should start with a shell balance. You take a shell. You say this is the Q at Z, QZ at Z, and this is the QZ at Z plus delta Z. And there's also heat loss to the surrounding, which can be calculated using Newton's law of cooling, right? And you write down in minus out plus generation is equal to accumulation. The question says that it's steady state, so the accumulation is 0. Generation, there is no generation, there's no mention of generation, there's only ins and outs. I have 1 in and 2 outs, and the in is QZ times the area is the cross-sectional area of the cylinder is the area of a circle, which is pi r squared. Pi r squared. Estimated at Z minus the conductive term, which is going out, QZ pi r squared at Z. Okay. Plus, or sorry, minus, there's this out as well, which is H times the area. The area of this, I mean, the area corresponding to this flux is basically this area of this ring, right? So it's basically the perimeter, which is 2 pi r, times the thickness, which is delta Z, because this is my delta Z thickness. This thing has a thickness of delta Z. Okay, that's equal to 0. Those are all the terms. And if you divide by delta Z, and take the limit as delta Z goes to 0, you find that the negative derivative with respect to z of qz pi r is equal to, these cancel, and you get h 2 pi r. Okay. 2 pi r. Oh, this is pi r squared. Okay, good. And from here you get negative dq over dz is equal to h 2 pi r over pi r squared. Well, basically we found exactly the same equation in our slab case. Remember, in our fin we had this in this fin example, but instead of 2 pi r we had our perimeter there. I mean, the perimeter was different in that case. It was 2 times v plus w. But it's just the perimeter, and instead of pi r squared we just had the b times w, which was the area, right? So it's basically the same equation, but instead of like 2 pi r we had the perimeter of the corresponding geometry and the area of the corresponding geometry. So this formula is a general formula for any shape of fin. Okay.
Should the h term be multiplied by t minus t infinity?
Oh yeah, that is. Yeah. T minus t infinity. Exactly. Thank you for this very important correction. Okay, there you go. But for our case, the perimeter divided by area is just, as you can see, the pi's cancel, one of the r's cancel, and you get h 2 over r, or let's say 2h over r, t minus t infinity. Okay. Not solved yet because I need to get the temperatures, right? I need to get the temperatures. So I should actually follow similar to what we have done in the class. Now I'm going to write down the Fourier's law. Plug in the Fourier's law. Minus k dt over dz. I know that there's no flux along the r direction, conductive flux along the r direction, so I'm just going to assume the temperature is only varying along the z direction. So if you plug this in, you get k plus k, the second derivative of the temperature is equal to 2h over r t minus t infinity. Okay, and this is a function of z, and this is also a function of z. So I need to actually collect them in some way. But I think it's better to simplify it by, remember we actually labeled this, or at least a similar term, or maybe, let me just get the k to the right-hand side. So get rid of the k and put it in the denominator here. And let's call this thing lambda squared, as we did previously for the same reasons described in the class. Okay. Okay, so you get And also we need to non-dimensionalize. Non-dimensionalize to make it simpler. Theta t minus t infinity divided by so I have another temperature here, TL. Let me use that one. TL minus T infinity. Okay. And the Z can be easily non-dimensionalized by dividing by L. Okay. So the new form of my equation is going to look like, let me just work on it a little bit. So if you divide both sides by TL minus T infinity, so d squared theta over d z squared, this becomes lambda squared theta. And instead of the dz squared, you're going to have like double derivatives with respect to z, but the dz is nothing but L times d psi. So you can have d psi squared here and 1 over L squared is here. And then your equation will be d squared theta over d psi squared is equal to lambda squared L squared theta. Okay. And you know that this has a solution as we described in the class as theta is equal to, this is a positive number. So you're taking the double derivative of a function and you find the function itself up to a positive multiplication factor. This can only happen with the exponential functions. This cannot happen the sine and cosine functions, because the sine function, if you take once, you get the plus cosine. If you take twice, you get the minus sine. So it gives you the minus for the cosine as well. You take the double derivative of the cosine, you get the negative of the cosine. So it doesn't work. So it should be the exponential functions or the hyperbolic sine and cosine functions. So you can actually write it as C1 sine hyperbolic lambda L psi plus C2 cosine hyperbolic lambda L psi. Again, this same solution. We need to find the C1 and C2, right? What are our boundary conditions? I should use my boundary conditions to find C1 and C2. Now, the first boundary condition is at, let's see. Okay. At Z is equal to 0, the Q is equal to, or QZ is equal to Q0, right? It's given. And then the Q, you can write it in terms of theta as well. We know that the Q is equal to negative K dt over dz, correct? In the dimensionless quantities, you can multiply and divide by T, what was that? TL minus T infinity. TL minus T infinity divided by L, okay, d theta over d psi. Okay, and you calculated that z is equal to 0, so that means you calculate this at psi is equal to 0. So this boundary condition is basically nothing but d theta over d psi at psi is equal to 0 is equal to, if you use this and this, you can take these to the left-hand side, making them upside down. It's going to be negative Q0L over K TL minus T infinity, right? So that's their boundary condition. So let's make use of this. So the derivative with respect to psi is nothing but the C1 cosine hyperbolic is C1 times lambda L cosine hyperbolic lambda L psi plus C2 lambda L sine hyperbolic lambda L psi, but the psi is 0 because I have to calculate that 0. TL minus T infinity. From here, this term becomes 0. And then this term becomes 1, right? So from here, you get C1 is equal to, the L's cancel, Q0 over lambda K TL minus T infinity. Correct? So we found the C1. Now we should find the.
You're missing a negative sign.
I'm missing a negative sign, yeah. Okay, yeah. Good, so boundary condition 2. At Z is equal to L, or in other words, as psi is equal to 1, T is equal to TL, or in other words, theta is equal to 1, right? Yeah. Okay, good. And yeah, let's get this equation and plug in the numbers. 1 theta is equal to 1, and that's equal to C1, which we found already as Q0 over lambda K TL minus T infinity times sine of lambda L, sine hyperbolic, I'm sorry. Yeah. Sine hyperbolic of lambda L plus C2 cosine hyperbolic lambda L. From here, we can calculate the C2 as well. C2 is 1 plus Q0 over lambda K TL minus T infinity sine hyperbolic lambda L divided by cosine hyperbolic lambda L. That's C2. So we found the C1 and C2. Good. Okay. Any questions so far? So
yes, I have one question.
Yeah, sure, go ahead.
So my question is, I kind of got lost how we went from the first derivative to the second derivative, or like the kind of why do we do that step?
Yeah, so let's see. Our second derivative is in our governing equation, Domingos, right?
No, I'm saying the one on top, where we have dt. Yeah, I kind of didn't understand
okay.
where I went from
Sure,
dq to the
sure. Yeah, sure. So let's put a side note there. So if you use the Fourier's law, this one, right? And if you plug it in here, Domingos, and you get the following: negative d over dz, and instead of the q, I'm going to write this thing, negative k dt over dz, correct? On the left-hand side. Is that clear?
Yes, my question was like, why do we don't use like the integral to find? That was my question. Like, why we don't use integral in this case, but in the other ones we use integral?
Oh, okay. So you're asking why am I not solving for q before I plug in the the Fourier's law. Is that your question?
Yes.
Okay,
Yes.
excellent question. The reason is the following, Domingos. In the earlier examples, on the right-hand side, there was nothing which actually, which is a function of c that you don't know. Now, t is a function of c and you don't know what it is. If it were, for example, z squared, if you knew it, yes, you would be able to. But you don't know how t actually changes with z. That's the problem. So you're not going to be able to take the integral with respect to z, the right-hand side. That's the issue. So let me show you. Imagine that you're actually following this procedure. dq is equal to negative 2h over r, t minus t infinity dz, correct? And you take the integral of both sides, Domingos, right? The problem is you don't know what this is. You don't know how it changes with z. So you're not going to be able to find this integral. That's the problem. Okay?
Okay.
So you should actually find this term in terms of t so that you can actually combine all the t-dependent terms and find t as a function of c instead of q as a function of c. Okay?
Yes.
Another question, sir.
Sure.
So if we were to put in q as equal to our Fourier's law, which is negative k dt over dz,
Yep.
we then can integrate it to find the temperature, right?
We then collect all the temperatures on one side and all the like z's on the other side. But no, well, actually, you get one equation with one independent variable. But here in this equation, you have two independent variables, q and t, that complicates the things. And by plugging in as a function of derivative of the t, you actually get an equation, this one or this one, which gives you the functional form of at least the second derivative. I mean, which gives you a differential equation which can be solved.
Okay. So then we just put it back to non-dimensional equation to arrive to to a solution for that.
Yeah, exactly. Or you can say this is also a trick in differential equations as well. You can say, let me change my variable, let me call this y, and then this dt is going to be dy, so I can actually use y here. You can also do that if you like. And then that's going to be also easily solvable problem. Right?
And how do we know when we need to non-dimensionalize an equation, something like that? Or
I would say non-dimensionalization almost always helps simplification.
okay.
For this particular problem, the main issue is having t here, but having the difference of the t here. So making them on the same footing, we change the variable. Not necessarily you need to non-dimensionalize, but the non-dimensionalization help you in many ways. One, it's going to be easy. It's going to make it easier to follow the units. For example, if you have a look at this thing, you know that this is entirely unitless and this is entirely unitless, and you know that this must be unitless, so that you can go back and check whether this lambda square is indeed 1 over meters squared. You can go back to your definition and you can see that, yes, this is 1 over meters squared. Or another way it helps is, non-dimensionalization helps is it makes the equation simpler. Okay. And as I said, you don't need to for this equation, but it just makes things simpler and track the dimensional analysis in a simpler way.
Understood. Thank you.
No problem. And also, non-dimensionalization helps you to generalize your solution so that you can apply it to any problem. I'm not talking about the test problems, but because generally when you try to solve the problem for the test, you don't care about whether you're going to use that result later or not. You just want to get the highest grade. But generally, we get used to doing non-dimensionalization to make our solution more generally applicable or transferable to other problems. Okay. Especially, I mean, when you solve a differential equation analytically, generally it doesn't matter. But if you are going to use numerical techniques, and for example, imagine that you're plotting the temperature profile, right? And imagine that this is meters, this is kelvins, and you have a 1 meter long rod, and imagine that the temperature distribution is this, right? 1 meter. And nobody's going to care about this solution because they're going to say, oh no, I have rods like 1 nanometer rods. I cannot use this solution that you came up with. You're just giving me a graph or a table with some numbers, and it doesn't make sense because it's not applicable to my situation, because it's not an analytical formula, it's a numerical solution. But you can say, oh, in non-dimensional units, it's theta versus psi, and this is 1, this is 1, and my temperature profile is this. And you can apply it to your nanometer system as well, because you can just resize your system and find out your corresponding z, depending on your dimension, and you can calculate for your corresponding temperatures. So that's such a neat thing to do. Does that make sense? So this one is not generally applicable. But this is generally applicable. Does that make sense? When you solve the problem numerically, especially. Is that clear?
Yes, sir.
Okay. Okay, so we had found the temperature profiles. Yeah, the only thing you need to do, you just plug in those C1 and C2 in this theta expression, and that's it. That's your temperature profile. Part B, using the relation obtained in Part A, derive an expression for the steady state heat transfer rate between the rod and air. Oh, that's difficult. How are you going to do that? How am I going to be able to get the total heat transfer rate between the rod and the air throughout the entire surface? Yeah, that's a tough thing to do, right? I mean, look at that. So you should get like H time, like for the if you do the shell balance, if you commit to the shell balance that you did and like add up all the entire heat lost from the surface, you would get something like the dq convection, the heat loss through convection, is going to be equal to H times the infinitesimal area, which is delta Z times perimeter, which is 2 pi r, times T minus T infinity. So basically this delta Z is nothing but dz, right, for our case. And you integrate from 0 to L, the dz, and this is going to be your total from 0 to total. And then you would get like the total Q lost by convection must be equal to 2 pi r h integral T minus T infinity dz 0L. That's gonna be, I mean, oh my God, you're gonna plug in these numbers and take the integral, plug in those C2, C1, whatever, and take the integral. That would not be really convenient, right? But you can actually commit to, so this looks difficult. You can do it, but that looks difficult. Another way, an easier way is to do, you can commit to energy balance. And you can say that here's the rod, right? And let me take my system as this entire rod, my system. And let me actually decide like all the inputs, all the outputs, and so on. And this is the Q0, my input. This is QZ at L, Z is equal to L. And that's the total Q lost to the surrounding. So I can find the Q loss from the energy balance. I can say Q0 times, so in minus out, let's say. In minus out plus generation is accumulation. And in is Q0, the flux times area, pi r squared. Minus 1 out is the Q lost to the surrounding. And then the other out is QZ times QZ at Z is equal to L times pi r squared is equal to 0. So from here you find Q lost as pi r squared minus Q0 plus QZ at Z is equal to L. So you can calculate the QZ at L pretty easily by taking the derivative of this thing, right? QZ at any Z is basically nothing but this we had found earlier. Divided by L. D theta over d psi. And that's equal to C1 lambda L cosine hyperbolic lambda L psi plus C2 sine hyperbolic lambda L psi. And QZ at L is going to be equal to, for psi is equal to 1. So that's equal to negative K TL minus T infinity divided by L. C1. I can take the lambda. So this is lambda. There is lambda L here as well. So I can take the lambda L outside of the parentheses and get rid of the L's. C1 cosine hyperbolic lambda L plus C2 sine hyperbolic lambda L. So that's QZ at L. And then you plug in this formula. Then you find the Q lost is equal to pi r squared minus Q0 minus K TL minus T infinity lambda C1 cos hyperbolic lambda L plus C2 sine hyperbolic lambda L, where C1 is equal to, was found as negative Q0 over lambda K TL minus T infinity and C2 is equal to okay. So that's the solution. And that solves part B. Okay, now part C, just calculate the heat transfer rate if the Q0, TL, T infinity, R, L, H, and K are given. I just leave it to you as an exercise. You just plug in the numbers. So part D. So let's say part C left as an exercise. Part D. We assume that the temperature is function of Z position only and can be considered uniform for a given cross-section of the rod, which implies that the thermal resistance within the rod is negligible compared to thermal resistance between the rod, surface, and air. Check if this assumption is valid in this case. So which number should we calculate to check this assumption? Any idea? We have done something similar in unsteady state heat transfer. We said there is a way to neglect the internal resistances, internal heat transfer resistances. And for example, the material, the solid material is very conductive like metal, and it's large with respect to the heat transfer rates or the heat transfer coefficient between the fluid and the solid. What did we say? With which number did we look at?
The bio number.
Exactly. So we are going to check the bio number. And if it's much, much less than 1, check if bio number is much, much less than 1. If it's much, much less than 1, that means that the cylindrical rod is so conductive that you can neglect the internal heat transfer resistances, so that you can assume a uniform temperature profile along the R direction, but not along the Z direction. So I'm going to calculate the bio number, which is H times L characteristic divided by the conductivity of the solid, not the fluid. If it were the fluid, it would be Nusselt number, but we don't care about the Nusselt number now. We want to use the solid conductivity. And the L characteristic can be anything that tells us the heat, tells us anything about the dimension along the radial direction. right? Because I'm not talking about the heat transfer along the z direction, but heat transfer along the r direction. So when you take a shell, for example, right? When you take a shell like this, and for this heat transfer along this direction, what is the characteristic length? You can just take it as radius hr over ks if you like, or you can say I can use the area divided by the perimeter, right? Because like if you think about the normally the length characteristic is volume divided by area, right? But the volume of this shell is the area, cross-sectional area, times the delta z, and the surface area is the perimeter times the delta z. So you can say that, let me take a cross-sectional divided by perimeter, which is basically pi r squared divided by 2 pi r, which gives you r over 2. So you can also take the r over 2. Doesn't matter because you're going to do an order of magnitude estimation. You can take either this or hr over 2. Either is fine because we are trying to compare whether it, like, we are going to understand whether it's 1 or 0.00001, or maybe but if it's for example 0.5, I'm just not going to assume that it's much less than 1. So I'm just thinking about order of magnitude estimation. So it doesn't matter whether you have this 2 there or not. And the h is given as, let's plug in the numbers, 54.5 in SI units. The radius is 2 centimeters, 0.02 meters, divided by 2 times the conductivity is 150 watts per meter Kelvin. Watts cancel, one of the meters cancel, and then this meters cancel, this Kelvins cancel. It's a unitless number as promised. So what you get is, let's calculate, 54.5 times 0.02 divided by 2 divided by 150. So it's something like 0.0036. So if I had not used this 2, it would be 0.0072 something. It would not change my conclusion that this is much less than 1, because practically this is less than, when it's actually less than 0.1, you can actually assume that it's much less than 1. Okay, good. So this is a good assumption. We say that, yes, this assumption is valid. So you can assume is valid. So you can assume temperature does not vary significantly along the r direction or radial. Direction. Okay, so that ends all the problems.
So since you said this is the last problem, could you go over like a problem regarding boundary layer conditions or a heater?
Sure, I can go over. Okay, which one do you prefer?
Boundary layer.
Boundary layer problem. Okay, so let's do 19.11. Okay. It says a plane surface 25 centimeters wide has its temperature maintained at 80 degrees centigrade. Okay. Atmospheric air at 25 degrees centigrade flows parallel to the surface with a velocity of 2.8 meters per second. Using the results of boundary layer analysis, determine the following for a 1 meter long plate. Okay, so we have this L is equal to 1 meter. Air is flowing. Okay, imagine that this is your boundary layer for the boundary layer for the momentum transfer. So let's calculate A, the mean coefficient of skin friction. Okay. So first thing you should calculate is the Prandtl number of the air, right? Because you want to actually, so in A it doesn't ask you this Prandtl number, but so to clarify it, CF, mean coefficient of skin friction. Okay, so just give me a second. There's I think there might be some ambiguity about taking the mean or the average of the skin friction. Okay. In such problems, you should first have a look at the Prandtl number. For the air, it's something about 0.7. It's ambient conditions. If you don't know it, you can actually calculate it using nu over alpha. And you should actually, it should be either given in the problem statement, or you should use your textbook appendix, where there are actually thermodynamic properties of the air and other substances. If you don't have if you're not given the nu and alpha, you can write them in terms of mu and other quantities. For nu is equal to mu over rho, and alpha is equal to k over rho Cp. And you don't need to know the rho because they cancel. You can also use mu Cp over k. So you can use either of these equations, any of these three equations, to find out the Prandtl number. So if you plug in the values for the mu, Cp, and k, you will find out the Prandtl number of the air is something like 0.7 at 25 degrees and 1 atmosphere. So that tells you something. If you go back to your notes, when Prandtl number is almost equal to 0.7, you can use, so So that's the, yeah, so this is the skin friction coefficient. So let's calculate the skin friction coefficient for the entire thing. Okay, so CF. Okay, so we're going to use this lecture 10, page 2. 646. CF is equal to 0.646 Reynolds number L to the power 1/2. Okay, so let's calculate the Reynolds number. L, let's write it here, is V infinity L over nu for the air. Okay, so you should actually check the properties of the air. It should be given somewhere in. It's not given in the problem statement, I guess. Okay, so you should check your textbook, or maybe I should find it from the example problem. Yeah, in problem 7 it's also given. You can check that. It's at 27 degrees centigrade, but that doesn't matter. It should not change that much. The kinematic viscosity is 1.5 10 to -5. Meters squared per second. V infinity is given in this problem as 2.8 meters per second. L is given as 1 meter. We get 2.8 times 1, 5 times. Okay, so you get something like 187,000. Okay, unitless. And then the CF L comes out to be 0.646 times 87000 to the power 1/2, or -1/2. .646. Okay, so you get something like 1.50 times 10 to the -3. Okay, that's the skin friction coefficient. Now, in part B, it says, what is the total drag force exerted on the plate by the air flow? So you check the drag force formula that we had already derived. So it's the so you can either use the drag coefficient and multiply it with the average kinetic energy to find the drag force, or you can just use this formula as is, and the B is the width. So it's maybe it's a better idea if I pull them in my notes. This is lecture 11, page 1. There you go. Okay. I think it's a better idea if we use the CD, this thing. Okay, so let's do it that way. First, calculate the CD. CD is equal to 1.292 Reynolds number to the power -1/2. And from here you get the power -1/2 times 1.292. So CD comes out to be 2.99 10 to the -3. But the drag force is going to be the area times, let's write it. Okay, it's the area times the CD times the average kinetic energy, 1/2 rho V infinity square, average kinetic energy per unit volume. Okay, so FD is equal to area of this plate is B times L. FD is, B is given as 25 centimeters. Which is 0.25 meters. L is given 1 meter. CD we calculate 2.99 times 10 to -3 unitless. 1/2 rho of the air. You should find it somewhere. Let's see. Okay, it should be something like 1.2 kilograms per meter cube air density. V infinity is given 2.8 meters per second. Yep. So you get FD is equal to, so the algebra 0.25 times 2.99 times 10 to -3 times 1/2 times 1.2 times 2.8.
The 2.8 needs to be squared.
Yeah, that's exactly. Thank you. Times 2.8, another one. Okay. 3.52 times 10 to -3. Let's check the units. Meter squared here. Meter squared times kilogram meter cube meter squared over second squared, and you cancel 2 of them. Here you cancel 1 of them. You get kilogram meter per second square. That's the unit for the Newton. That's identical to Newton because you know from F is equal to MA, right? That Newton is identical to kilogram times meter per second square. So that makes sense. So this is Newtons. Okay. That's the drag force acting. And part C, the total heat transfer rate from the plate to the air stream. So we need to find the H. We need to know the H for this, correct? Because we know, sorry, we don't know the Q. We want to calculate the Q. We want to we know the area, we know the temperatures, but we don't know the H. But the way to find out the H, we need to find out the Nusselt number. And to find out the Nusselt number, we're going to use the Reynolds analogy, right? Let me show you that part, Reynolds analogy. Okay, there you go. If the Prandtl number is approximately 1, we said we can use the Reynolds analogy. For this case, it's a perfect example because the air has a Prandtl number almost equal to 1. It's 0.7, so it's very close to 1. So you can use the Reynolds analogy. So the Reynolds analogy says that the Stanton number is CF over 2, which is the Nusselt number over Reynolds Prandtl. So Nusselt number over Reynolds Prandtl is equal to Stanton number, and that's equal to the skin friction coefficient divided by 2, right? And we already had calculated this in part A, right? And Reynolds number we already calculate. Prandtl number we know. So if you plug in the numbers, you're going to find out that the Nusselt number divided by the Reynolds is 187, was that? 187,000 times 0.7 is equal to CF, which is 1 point from here, 1.50 times 10 to negative 3 divided by 2. So let's find out the Nusselt number. Okay, so I can get rid of these 3 zeros and these, and you multiply them. So you get 7 times 1.5 times 0.7 divided by 2. You get 98.2 unitless. And we know that the Nusselt number is equal to H length characteristic over K of the fluid. Okay. For this geometry, it's HL over K. HL over K fluid. Now let's plug in the numbers. Now the Nusselt number is 98.2 unitless is equal to H. We want to find out. L is 1 meter divided by conductivity of air, K. So I should find it in the book. So let's see. Let's go to appendix. Let's see. Physical properties of gases and liquids. Air, the first one of them, appendix I, page 731. At 300 Kelvin, the conductivity is, they're given, it's the 100 times the value is given, so I need to multiply by 10 to negative 2. So this is 2.624 times 10 to minus 2 watt per meter Kelvin. In the book, it says conductivity times 10 to 2 is given as 2.624. That's why you need to multiply it by 10 to negative 2, make it K. I forgot. Page 731. Page 731. Appendix I in textbook. So let's solve for H. Times 4 times 10 to 92. You get 2.58. And the units is, since this is unitless, it's going to be watt per meter square Kelvin. And the meters cancel and you get this one. Watt per meter squared Kelvin. So we found the H. Now I can find out the Q. So the Q is equal to H A T surface minus T infinity. Oh, what was the T surface? Let me find the problem. Yeah, 80 degrees centigrade. Q is equal to A is 1 meter times 25 meters. Area of the plate. TS is 80 degrees centigrade minus 25 degrees centigrade. Again, the differences in the centigrades is the same as differences in the kelvins. So the unit of this entire thing is going to be Kelvin. So that's what, 55, right? 55 Kelvin. So if you do it, 2.58 times 0.25 times 55, you get Q is equal to 35.5. Let's cancel the kelvins, meters. You get what? Okay, that's it. So the total heat transfer rate from the plate to the airstream is 35.5 watts.